All right. Perfect. Jump to today. Who went first last time? Should we go in order again? All right. Group one, I think you guys know what to do, right? Give me 2 seconds to sit down and get ready to take notes. It's big. Enough. All right.
All right, hello everyone. This is the update from Group 1. So in this week, the spree lesson was bad job, so we were able to work on the G-tools and the star machine or something. We successfully did the 2 holes on this start piece. For the EDM, we haven't done EDM yet because we still trying to figure out the Esprit setup with Joe. We also we have the start here, so it's a 3-inch by 6 feet start. Then we just need to try to do 2x3 in the workpiece and drill a hole for the wire. And then we meet with Joe to talk about this Esprit setup. My old Esprit has some problems, so when you do Esprit, then load it out to the NC code. You want to make sure you have M20, M21. After, well, M20 is thread wire, M21 is charge wire. So you want to make sure if the wire is going to pass through something solid, you want to make sure those 2 line there, so it has wire, don't just drag the part out. Because if you don't do that, you will just the wire will just drag the entire part out of whatever your holder is. Also, slot stop, because apparently when you use EDM to charge the part, the pieces don't really fall out. It kind of twist and they stuck in there. So if you don't use the slot stop and manually push whatever you cut out, it will toss the wire, and again, it will drag the entire piece out with all the force the machine can have and the wire can handle, and that will completely drag your part out. So this gear, I will pass it down later, is what happened when it dragged the part out. So it tossed the inside the hex piece, but the inside the hex didn't fall out, so it's wire caught on the hex, and it drags the entire thing out. So pretty much drags stuff at an angle, and come back and cut again, so the hex is not centered. That's what will happen if you don't, make sure the wire didn't cut anything. Also, you want to make sure, I don't know if you mentioned it the first way, you want to make sure the wire was electrified before it touches the piece. Otherwise, you will just short the machine, and that is not good. So when you do a spray, every operation, the wires enter, you want some lead-in distance. So it started energized before it come in contact with the piece. And we also started how-to guide. We haven't finished it, but we started it.
All right, so this was our outsourced price. We did try to go through exometry, but every time we selected EDM and then we went to go get our quote, it kept changing it to selective latent engineering or some other type of 3D printing process. So we couldn't really get an exact exometry quote. So we just went to McMaster. I got the part number. So that was around $31.85. That was the best we could do with that.
So there are some challenges. As I said, if spray was done and come back up, then the G-code will have problems. So the wire can then get caught on the part if we're not careful. Also, when I drew this part first, I've messed up the Z offset. So when you do the what's it called, the drilling pulse and the mill, you need to be careful because it is a very thin piece, and make sure you set up the correct and make sure all your offset are correct. Otherwise, it's not that hard to just mess it up.
These are our goals for this week. We got to meet with Joel again Thursday or Friday because we finally have our Esprit hopefully running now. So we want him to recheck it and run the EDM to see if our part will work. And we've been starting to capture more like process for the guide because we realized we've been slacking on that lately. And that's it.
Oops. Thank you very much. Any questions? And I passed around the part we made, so if you guys can give it a look, and if anything you're not clear, just ask.
Questions? No.
I was just playing around with the gears and the tolerance level, like when they're close together, a little tight. Are they going to be a little bit further apart?
I mean, if you shove them together, they're not going to spin well, but you're not supposed to shove them together.
Just making sure.
Yeah.
It's hard to visualize.
That's whatever the team doing the base job to make sure they're the right distance apart.
How did we specify the correct distance? Did you tell them what the spacing was?
I gave it a number.
Okay.
So did you guys have that? It was 0.75, right?
Yeah.
Anyone else?
I have a comment.
Yes.
The Esprit license was down for about 12 hours.
Yeah.
So it's probably not still a topic of conversation.
It was the one day we went to
One
go.
day.
I know. But it was like 12 hours.
But
It was the full 12 hours we needed.
16 hours. I'll give you 16 hours.
All right. We'll take it.
So any questions? Also, we need my poor part back. So.
And so it was the part dropping out that
Yes.
causes your problem, right? So when it cuts all the way around and cuts through, if you visualize, and every class can sort of visualize that last instant before it cuts off and draw a free body diagram of what's going on, it makes sense that it's going to tip. If it tips, it's going to get caught, and if it gets caught on the wire, then that's what caused it to move your part.
Yes.
And that's exactly the same thing that happens if you're doing a cutout like that in a milling machine. And so in the wire EDM, it either breaks the wire or it drags the part. In the milling machine, it either throws the part across the machine because you got so much more cutting force, or it breaks the tool. So same problem both in the milling and in the EDM. And just like in the milling, you need to have a lead in. You need to approach the part. You can't just start at the part.
Yeah.
And so you need that. So it's very, very similar overlap.
Any question from the other group?
All right. Who's next? Group 2? Numero dos.
All right. So this is our third presentation for injection molding. This week we haven't gotten terribly much done. I know personally I've been busy. I don't know about everyone else, but we were able to update our CAM and order the stock for our part. But that is mostly what we've gotten done. And then just another little demonstration of how this will work. So it fills in the mold there, mold comes apart, and then if you had ejector pins, you would push from here and the part would pop out.
You can use fingernails instead of injector pins.
Yeah, the way our part is
Yeah, it's pretty small. I think it's easy to pop out.
yeah. Same thing.
Same thing, we talked about this last time, how exactly it works. If this one again is a automatic one, we're going to be using a manual press rather than, so basically we're going to be just putting the plastic in the feed hopper there, it's heating up in the cylinder or barrel. And you put your mold in the clamp down at the bottom there. Then once it's all heated up, you use a press to force the melted plastic into the mold. Wait a bit for it to cool. Then you pop the part in the mold, and you got your part. And you have to cut off the little anything that's extra on it. So here's our example. So just to answer some questions that we got from last time. So the reason we're using the plastic we are, I can't remember the name right now.
LDPE.
Yeah, that's just what's available. So
It's because we have a big bag of it, and I told them to use it.
yeah, that's basically why. There's not really any reason. So it is going to be a bit of a struggle because of the large size change we're going to get, but that should be relatively easy to compensate for with just making our mold a little bit bigger. So that shouldn't be too bad. And if our part ends up being a little bit too big, that should be fine since plastic is relatively easy to deform. So we should be able to just push it into the holes regardless. So we also got a question of how hot it needs to be. I did some quick searching. So I believe what it said was, I think 180 to 280 degrees Celsius. You need to heat up the plastic to get it to injection mold. I think we're going to have to do a little more research to see exactly what temperature we need for this, but it seems, at least from what I saw, it was a pretty wide range of what we're able to do. And generally, it doesn't take very long to actually do injection molding. It's just the plastic. Once the plastic is melted and you got the mold in there, it's just pushed down and it fills up pretty quickly. After that, it's just waiting for the mold to cool, which could just take a minute if you're cooling it down. It could just take a few minutes. So it really doesn't take that long, which is why these parts are pretty good for large volume stuff. No, we're not doing that. I think those were the major questions. Anything else that for now? Yeah.
I don't know if have you planned out how you want to make the mold?
Quincy has started doing the cam for it. We had the SolidWorks file set, but I have an idea of what we want to do.
Yeah, we haven't gotten a chance since we're waiting on the actual material.
Describe the material.
Aluminum.
What shape?
It's a 2.5 by 2.5, and then 1/2 inch thick. And we'll be milling like a 1/4 inch down into it, so it probably doesn't need to be 1/2 inch thick, but
Because we have a whole bunch that's
just
2.5 by
like
3/4
Yeah.
thick. We have 20 or 30 feet of it, so you probably could have borrowed some of that.
Okay.
So if the injector it's manually operated, that essentially means that once you've made the mold, there's no longer a computer component to the process for you, right?
Basically,
With the tool that they're using.
Yeah.
But in production, they're automated.
Yeah, pretty much.
But yeah, the computer aided manufacturing part is really the mold.
I mean, we use
Design
a
and
computer to set
manufacturing.
the temperature. So,
This computer.
well, there's a computer in there. Sure, to set it to the right temperature.
Yeah, so I think you could grab a piece of scrap off the scrap cart to cut a test part, make sure that your stuff goes together, make sure your pins go in the right place, all that stuff. Did you have to order pins, or are you just using something we found?
Probably just find something.
Okay.
Cut it down.
Just plenty of pins.
Anything else?
Say again? Oh, there's dowel pins. Is that what you mean? Yeah, there's plenty of dowel pins that you could use for this.
1/4 inch diameter, at least an inch.
Yeah, there's drawers full of them.
Awesome.
But that sounds like one that we would have.
Yeah.
All right.
Thank you.
Group 3.
All right, so fourth axis lathe group is back. One thing to pay attention to that we kind of added into this presentation was some big bold red text on the bottom. Made some mistakes while we were milling this week, and we could have either hurt ourselves or completely damaged the machine. So just pay attention to those things. So I believe we talked about this last week, but kind of the first thing a user would have to do when operating this lathe is adjust the chuck jaws. And so we've got some pictures over here and have a guide of kind of how far down you should put these jaws so that they clamp the workpiece securely and safely. So you ideally want to have the biggest part facing in so that it holds on to the most amount of surface area of the stock. And then you want to have 8 teeth showing up here. It's a little tedious to do, but if they're off by 1 or 2 teeth, it could spin out of control and be a really bad day. And then you torque those down to 79 foot-pounds. There's a torque wrench right there on the lathe.
So one of the first parts that we had to learn to do on actually the smaller mill, the fourth axis, which is kind of the same process as the fourth axis mill, is doing the tool offsets, and this is making sure that the tool doesn't hit the back of the chuck. So it's kind of a list of steps you should follow. You can kind of get into it more when you're in front of it. It's definitely easier to see when you're in front of the lathe, but it's making sure that this little dowel pin can just barely pass through and subtracting that from the CA face measure in order to make sure that that amount is set before you do any machining. So it's just very important to know that the tool is not going to hit the back of the chuck and damage that as well. And then another part that we did was loading these stock pieces. One of the main issues that we came across was really do not load anything longer than 8 inches into this feed. We accidentally loaded a 6 foot long bar, and the back had no guide, so it started making a really loud noise if you're really looking at it. And Rodrigo came by after a minute and said, "Yeah, you're probably gonna die or disrupt the machine because the back of the guide just started spinning and will like move the machine." He said it would turn into mist. So that was really good to know. We've actually cut out a few pieces of around this like 5 or 6 inch, and that should be plenty for everyone to use if we're machining ourselves. And also making sure that the length that you set out is no longer than around triple diameter, or else a lot of deformation will occur at the end. Yeah, so that's kind of just a picture of it in the, not in the 4 axis, but just in any kind of mill, making sure that that ratio of length to diameter is set.
So then similarly, the work offset, again, we can go into this more detail when you're in front of the machine because it's easier to kind of visualize, but this is basically telling the machine where the front face of the stock is. So that's like kind of your starting point. So the tool offset, make sure the machine knows where the tools are. The work offset, the machine knows where the work piece is. It's very kind of important to kind of mill off that first face so you get a flat face to start with, and we kind of work from there.
So a notable change we made this week is we changed our workpiece tool path where we went from Esprit to Fusion 360, and just for, well, actually that was only just because I could get a lot more help with Fusion rather than Esprit. And we do have to thank Rodrigo for that, for him helping me out with this, because he actually provided me with the tool library that I'd be using. It was notably easier to define the individual cutting operations, especially that particular part because we'll have the same way down the part until it reaches here and make that going this way as to the reverse direction. And the more detailed two-dimensional simulation is very helpful with that. Then you can actually invest and see. So I'll show you the lead in, so we're able to more accurately visualize how much space we need to give ourselves on the back end, so we don't get shot. And we can adjust the passes to make that kind of correct. So it started out too high, so I'm going to do that and make sure that we don't chamfer properly. And all that.
So this is just another thing that we're looking at. It's Virginia showed us how to import the programmatically from the Fusion 360 and Easter files into the lathe. Again, like there's kind of several steps and what buttons to press. We got two issues that we really ran into. Is really make sure that when you write the G code, do not have to exceed the maximum mark in the chuck. You realize that the spindle, like load on it, was bumping up to extreme overload and then falling back. And we stopped revealing like if the signal on for another minute probably would have exploded. Do not have it very high. Make sure it's kind of a level that chuck can handle and spindle can handle. Also, really do not remove, unless you download the program onto the lathe, do not remove the USB while you're using the lathe because that just like cancels everything and it's like, like two cars crashing into each other at 130 miles per hour each, so very dangerous. So try to avoid that.
So then the next thing we kind of have to look into here to do the hex shape of the shaft here is live dueling. So the fourth axis allows certain tools to be spun up to a certain RPM with keeping the workpiece stationary. So that's our next obstacle to figure out which tool, which angle we're coming in at, and kind of the CAM software behind that as well.
There were a couple of questions too about how the live tooling worked, and it's like these pictures will kind of show that with the fourth axis chuck, there is this part that is attached here, and these ridges interface with these to turn it from kind of that horizontal movement to that vertical. So that's the fourth axis, and this part was going to create the hex. As the piece is moving this way, this will come down, and we create the hex that way. Answers a bit more questions.
So that's the end.
So then we also just want to provide a more detailed drawing of our part with all of the sections to it. So the back end here on the left will be press fit into the bearing. This is kind of the lip here to make sure the gear doesn't fall off. Then we've got this piece here that will be hand threaded afterwards. There's a piece of relief over here as well so that kind of knob can screw all the way down. Then we've got a chamfer on this end to help the die go on there and not thread at a weird angle.
Did we mention that the removal of the threads in this design compared to the last one? So we're going to hand thread it.
Yeah.
So again, that's a tentative assembly for our RP3 part with T1's gear and the bearing in T4 we're using right now. There are still some problems. I thought we had another chamfer lip under that lip so that this wouldn't rise straight on the bearing, but I guess we don't. If we have to add that back, I guess we're going to have to. But it looks like we're probably going to have to slightly increase the diameter of that lip just so it's not awkward within the races here. And also, just trying to check the top machine here so if it actually works. Other than that, definitely an improvement from RP2 design.
So then this week we successfully milled our first little test part without the hex, so I'll kind of pass it around. Pretty small. So
It's hot too, apparently.
but there's a few things we have to clean up on it, which we'll kind of do next week with the cutoff piece and where that all lies.
This is just kind of the general process plan based on how much it would cost to do it on optometry. So pretty expensive fees. And then like our general task next week, we just really need to learn more about live tooling. Rodrigo said that the live tooling parts of it were set up or were broken in the fourth axis, or he just had like he said it's something for next week. We're there on Tuesday, and then there's some issues with the probe, I think. And
There is no probe.
well, he said
That's the-
it's not a this thing. So definitely next week we'll get that figured out. I think we really need to find the program in Fusion 360. You want to just run post processing and making sure that there's all these things that the tool numbers are incorrect, so we have to go on and correcting the tool numbers and making those get the correct outputs of the tool. And then also making sure that there's things in place to limit the RPM value for the chuck with a G code and making sure that the tail stock doesn't forward when you're spinning it.
So those are all settings in Fusion.
Yeah.
The operator that's programming sets those values.
Yeah.
Well, that's what we mean when we
Yeah.
say define.
It's like so you have to do it like, on the machine rather
We
than G code. Like so it's just a lot more
You
complicated.
should be able to do it in Fusion.
Yeah.
Not
No, he's saying that you could because after you post process it, we just put it in a TXT. So he said if he had looked at that before putting in the program,
Yeah.
he could correct it there too.
yeah. So in general, I'll give Rodrigo some slack for editing the G code because he knows how to do it. But in general, always go back to the CAM software and fix the problem. Don't edit G code and then load the code on the machine. That's been a policy at WPI for the past 20 years. So use the CAM software to make the G code. If the CAM software can't make correct G code, don't use that software. So manually editing the code afterwards is high risk.
Yeah, it kept freezing up and then crashing the machine. So there were definitely a lot of issues with that. I think also we need to also the live tooling and if this prototype doesn't have the tax part, as we forget to get that this week. And then continue to refine my leading machine skills. I don't know if you've seen my missing part with the finish on it. It's just really not that great. So make sure that we do it.
What tool did you use for that?
The 55 degree,
Yeah.
that and the cutoff tool.
55. I haven't seen the part. I just saw the picture of it.
Yeah.
But if that was the 55-degree tool, it was broken.
Yeah, the chips that
Because
were
the
cut off.
tool dose radius on that 55-degree tool is much bigger than the valleys that I saw in the thing.
Gotcha.
I think you were using the 35-degree tool, which has a much finer tool nose radius, and then your feed was just so much that it made those grooves.
Well, it's not just poor surface finish. Cutoff also wasn't.
Yeah, I was just looking at the surface
You can
finish on
see
it.
it curves inward, which it's not supposed to do.
Yeah.
I start creating the final part and then the tutorial, finishing that up. So.
I believe you used the 35-degree tool, not the 55. And so for the back cutting, what tool did you use there?
That was the cutoff. It just cut off too far back rather than up against.
Well, no, I mean you're making the part in this order, right? So you come over here, and then you said you came back to clean up this edge. What tool did you use for that? The back side. Go back to your slide where you showed the tool path.
Pretty sure it was
Here's the cutoff tool.
Yeah, I was
the same.
asking that question.
Yeah.
So did you use one tool for the whole thing?
No.
You used the 55-degree tool to rough this out. That's the blue tool path that I see.
Yep.
And then you use the cutoff tool to come in and clean this up. This side, right? Cutoff tool to come in and clean this up and do the cutoff. Okay, that was what I was clarifying. Perfect. I guess you guys can sit down, but before the next group goes, there's a couple things. So you're good. Unless people had more questions for them. No, go ahead.
No, I just like your part is really small. Just and I noticed the I was touching part. They don't have a chamfer on the press fit side.
On the backside,
Yeah.
No.
we were supposed to. It was in the last one. The last design, I swear there was one.
In the cat file.
Yeah, so I don't know where it went.
Okay.
If the tool couldn't reach it, it wouldn't cut it. The CAM software wouldn't put it
Well, it's not in the design that we have in our slides either right now, so that's weird. It should have been there. We'll check that.
All right.
Have you guys tried to tap the thread?
No, not yet.
We were just doing it.
Yeah. So a couple of things. The so what they experienced was they put that long bar in, and it wasn't supported at the backside, and so when you spun it, it made a loud noise.
Yeah.
Everybody jumped. Somebody hit the E-stop.
Yeah.
Yeah. Yeah. Rodrigo said you guys hit the E-stop. And so the solution that you used was to cut the stock into smaller pieces, which when I pointed at the bar of material and said you can use that stock, that's what I meant was, the bit of it that you needed, not the whole bar at once. Clearly we didn't communicate well at that moment, but that's fine. But you can, 6 feet is too long, but you could have used a 4 foot long piece in that lathe because we have spindle liners. And so the spindle is 3.5 inches in diameter. And you take a piece that fits 3.5 inches on the outside and 1 inch on the inside, and then you're supporting it all the way around. And so the spindle liners is that particular lathe is designed so that you can stack up 50 of those 1 inch round bars 4 feet long and have it automatically feed them in. And you cut the part, it feeds out more, cut the part, feeds out more, cut the part, feeds out more. So for small prototype part, yeah, sure, just cut a short piece of stock. But if we were making many of these, you would definitely go with the long bar. And that's the other thing I wanted to point out. So there's 2 ways to fix the unsupported material problem. And I've seen people in production shops with much longer bars. And even bars that are longer than the end of the lathe that they put them in. And what they do is they have other pieces out there that contain the end of it and support it and keep it spinning true. So if you're supporting it, you can do that. And the other thing is that maximum spindle speed. So every lathe chuck is going to have a maximum speed it wants to spin. It's usually stamped right on the front of it. I'm guessing on that lathe it might be like 3,500. I don't know off the top of my head. But with that, the thing that makes those chuck jaws close is hydraulic pressure. And so the hydraulic pump, and you set the hydraulic pressure, you step on the pedal, the jaws close, and they continue pushing on the stock material with the amount of hydraulic pressure that it's set for. As soon as you spin the spindle, those jaws want to accelerate away from the center, right? So you get centripetal acceleration. And how much they want to move, like the force that gets reduced because of that is going to depend on the mass of the jaws, right? F equals ma, right? So that force is going to be the mass and the acceleration. The acceleration is going to be based on the diameter, the radius, and the spindle speed. So the faster you spin, the less clamping force you have. Every time with a lathe, it's just the way they work. So that's another thing that you want to limit that spindle speed. But you should have a setting in there. In Esprit, the setting is called maximum spindle speed. It's a very complicated term. I assume it's called something similar in Fusion. It might be max spindle speed, something like that. Machinists typically call it the clamp speed. And they just mean don't spin over that. I don't know why. I don't know where the word clamp came from, but that's so you'll hear words like the clamp speed. That's the maximum spindle speed, because the surface speed changes with the diameter, right? And the tools want to operate at a constant surface speed, and so when you're moving towards the center of the piece, the lathe will increase the RPM as you move to the center to keep the tool moving at constant surface speed. And that's why you have that clamp speed. Don't ever increase above that number. So just to clarify some of the things that came up. So what's your next steps? I forgot. You may have said, but I didn't remember.
I mean, when's the live tooling so we can make the real part?
Okay. I think you should make a few more round parts and maybe just use like even the SL10. You don't need to set up the ST30 just to get good at making those parts. Make sure we're hitting the right diameters and stuff and that the tooling is working. Because that part does look funky. So, all right, great. Team 4, right?
Are you gonna be?
You can go over the chamfer part.
Yeah, you may just have to refresh.
Have it refresh.
Oh. Yeah, and then hit speed grader.
Okay. Oh, there we go.
And then select your group there. Yep. You go down and click below that. It might just open a new tab.
This one?
Go back. View a new tab.
There we go.
On the last slide. All right, so fourth axis milling group. This week we didn't get too much done, but we just figured out how to mount the fixture plate in the mill and like how to just get it started pretty much. So firstly, we need to buy some hardware, right? The red circles are how we're gonna mount it onto the table, the fixture plate, and then we're gonna use 1.5 inch Allen key heads to bolt it in. Then with this, under it, there's gonna be T-nuts, so it's gonna be squeezed onto the table. And then these two bolts are gonna hold in the fourth axis, and that's the hardware there we're used for. But before you can even put this into the mill, you have to clean off the surface first. Firstly, what you're gonna do is spray with some WD-40. There's like a little like thing next to it, a spray bottle. Then wipe it off with a paper towel, take off like any burrs, any metal bits, anything that's on there. Then after that, you grab the stone, you apply even pressure on the whole table just to slightly surface it in. It's gonna be like slightly grainy, like a little bit metal's getting like shaved off, but just to like keep an even surface. Wipe it down again. You're gonna see like some black marks on the paper towel, obviously. Then you're just gonna repeat that process as necessary. It's like cleaning it off, spray, clean off, spray, clean off until there's barely any metal bits left. And then you can put this on there. After that, you have to square it onto the table. There's a tool there. I didn't put a picture on there, but I should have. But it's called square. Then you put it on the turret of the mill. And the way you mount it on the mill is a magnet. There's an on and off switch. Then basically, it just has like a long arm that can adjust in many different ways. And there's a little needle at the tip of it. And then you're going to align that needle on this edge. Because it's going to get the edge facing like outside the machine. And then what you're going to do is run the needle across this and see how much variance there is. And then depending on how much variance there is, you're going to there's a dead blow mallet that makes the machine. You're going to slightly tap whichever side needs to be tapped to make sure it's going to move on the
Dial indicator.
the what?
Dial indicator.
Yeah, the dial indicator, yeah. That's going to move a little bit. But on the dial, there's a bunch of different pins, just goes in a circle. And then ideally by the end of it, you just want to be 3 ticks off after running it across. Just barely anything. But yeah, we haven't done that yet because we just figured out how to mount it in there. Then by the time we finish doing that, next group had to come in. But yeah, we'll have more pictures stuff next week, how to do that, and more clear explanation.
Okay, cool. We also have the design of our fillet radius, which is like 0.03 inch.
Yeah. Slight modification design, just so it doesn't like there's no hard edges. But yeah, that's pretty much it.
Questions?
Oh, also the cost estimate for the car.
to manufacture it that far?
That was with the fillet.
Yeah.
It looked like in the last slide, your the bottom holes are just like kind of straight through, but you can see them through the other hole. That could be like a final product.
Enough what?
Like so, the bottom hole, as you can see on the right, they kind of like they go straight through. You can see them through the other side.
Yeah.
Are they gonna be like that on the final product?
And you can, yeah, but the reason why it's just like that is to minimize the size of this part because we're going to be using a cylindrical stock. So the higher it is, the bigger the stock needs to be. So just trying to minimize that. If it doesn't work for whatever reason, when we're going to run it, yeah, we could like slightly increase the height so it doesn't go through, but that's not really an issue. But yeah. And what's your question?
So we're trimmed base plate. So how many, wiggling room do you have? How many ticks can you have downstream?
Oh, 3 ticks. But I'll have pictures next week. But there's a dial, right?
Yeah, I know that.
Oh, you know? Okay.
Yeah, I know. I was wondering if how straight.
No, 3 ticks. That's what Rodrigo said. 3 ticks. But like he said, also like if you've been there for like 40 minutes trying to do it, and you can only get it within like 5 ticks, it's fine. But yeah.
Each time. So I guess just to add, I guess we should mention. I believe that we were told that each tick is like 1,000, so within 1,500 of across from the beginning.
Because it is going to depend on which dial indicator you use. We have one where each tick is half a 10,000th.
Okay.
Which is going to be more ticks.
Yeah. Gotcha. Yeah. Any other questions?
I have a question.
Yes.
You can go back to the last one.
This one?
Why is it a fillet?
I just chose that because it looks smoother than a chamfer. Is there any manufacturing reasons why it would be a fillet?
It's why the grumpy old machinists call you kids with CAD. And so who knows why it should be a chamfer instead of a fillet?
You can't make a fillet.
You can.
It's just harder. It's harder. It's easier to use a chamfer to have a drill mill.
So if you put a 45-degree chamfer, you could make a 10 thou chamfer, you could make a 30 thou chamfer, you could make a 1/4 inch chamfer, all with the same tool.
Okay.
If you put a 30 thou fillet, well, when you need a 25 thou fillet, you need a different tool.
Okay.
Or you have to do a 3-axis machining operation to make it. And that's why your parts were $500.
Gotcha.
Because of the fillet.
Mhm.
And if that was a chamfer, they would have been $150.
Okay.
My guess.
Yeah.
Oh, and did you have the write something here on it? In the thing that you sent for the quote, did it have the engraving on the side
Yeah,
too?
it did.
Yeah. So they're expensive because they need so many different setups.
Mhm.
Or you need a much more expensive machine like a 5-axis or a 4-axis machine so you can hold it at one time. Any other questions? So yeah, if you change that fillet to a chamfer, the parts will be cheaper.
Okay.
My guess.
Yeah.
I don't know if the geometry algorithm would make them cheaper, but it should.
Yeah.
All right. That was everybody. Oh, what are you doing next week? What's up for next week?
Yeah, so now that we have the fixture plate set up properly, I believe Rodrigo just told us that the hardware that we actually need to secure it properly has arrived.
Okay.
So we can start getting work on test parts.
Okay, that sounds good. All right, so you're gonna make more test parts next week, or are you gonna make your first test parts next week? You're gonna make more test parts next week. You're gonna make more test parts next week, and
Should just make it today.
today and tomorrow.
Yeah.
So screw next week. We're gonna be done this week.
Yeah. But hopefully that's the goal.
And you guys are gonna make a mold test. Even if you don't have that stock material in, just get a piece of scrap and just make a test to make sure you can put it together. It would be nice to have that fancy squared up material for the finished product. Because what you're going to have to do is you're going to have to make that mold, squish it together in a vise, and do the injection molding into it. And could we hook up sometime tomorrow and get into the room and get that injection molding machine, bring it up to Washburn? So sometime tomorrow, probably afternoon. But anyone's the team. All right. Well, yeah, because I can get us access to the room to get it, or I can probably just get you access to the room to get it. Just email when you're ready to go pick it up, whenever it is. Email Adam Sears and he can call campus police and have them open it up for you. I'm sure they'll be okay. Keep me out of the loop. That way it doesn't have to be tomorrow. All right. Anything else? All right. That's what I have today. Thank you.
I just to be there for the setup.